All right, let's take a look at these practice problems, and I'm happy to tell you this is the last practice quiz where you're going to need a video like this. These are the last equations that you're going to be confronted with that are challenging. Okay, so let's take a look at this first question. It says if the peak wavelength of a star at rest is 550 nanometers, then what peak wavelength is observed when the star is traveling 150,000 meters per second away from the Earth? So these questions we can tell are dealing with the Doppler effect and how the wavelength of light is shifted when an object is moving. And the equation for the Doppler effect is given on the equation sheet is this. Delta lambda, the change in wavelength, over the rest wavelength is equal to the speed of an object divided by the speed of light, where the speed of light is a given value. It's given on the equation sheet. It's 3 times 10 to the 8 meters per second. Okay, so these are tricky problems. So here we go. Let's see what we're given here. It says the peak wavelength of a star at rest is 550 nanometers. So we're told that lambda, the rest wavelength, is 550 nanometers. And notice the question is asking us what will the peak wavelength be when it's moving. Now notice that delta lambda is the change in wavelength. But this question is asking for what will the new peak wavelength be. Okay, so that means we're going to need to take that wavelength and the starting wavelength and add to it whatever the change is. And that will give us what the new wavelength is, right? You have what you started at and what you changed by, and that'll give you your final value. Now another important thing here is that it's telling us that the star is traveling 150,000 meters per second away from the Earth. Away is telling us that this is red shifted. Remember, when something is moving away from you, it shifts toward the red or towards longer wavelengths. When it's traveling toward you, it's blue shifted, so it's traveling towards shorter wavelengths. So there's a lot of information being given in here. We're also being given V, that's 150,000 meters per second. And C, the speed of light, is given to us by the equation sheet, 3 times 10 to the 8 meters per second. Okay, so what are we trying to solve for? Well, we need to solve for delta lambda in this case. So, and that'll often be the case. So to get delta lambda by itself, what I'm going to do is multiply both sides by lambda. So the new equation after I do some algebra here is going to be that delta lambda equals lambda times V divided by C. Now keep in mind here, this delta lambda, that's all one symbol. It's not two different symbols. We're treating it as though it's a single symbol, the change in wavelength. Well, I have these three values. I know what lambda is, I know what V is, and I know what C is. So I can just plug these in, right? And I can leave it in nanometers even, because that's just going to give me the change in wavelength in nanometers. So 550 times 150,000 divided by 3 times 10 to the 8. And let's see what that gives me here. 550 times 150,000 divided by, I'm going to use parentheses again just to help me out, 3 times 10 to the power of 8, close parentheses, enter. Okay, and I get 0.275. 0.275. Now that's delta lambda. Keep in mind that this question is asking for what is the peak wavelength observed when it's moving that fast. And it's red shifted, so it should be bigger than the original value. So that means that this is going to become lambda plus delta lambda. Lambda plus the change in lambda, which is 550 plus 0.275. So my final answer then would just be 550.275. Okay, and that should be our value. All right, let's take a look at the second question. If the peak wavelength of a star at rest is 725 nanometers, then what peak wavelength is observed when it's traveling 800,000 meters per second toward the Earth? So this is very similar to the last question. I have here that lambda equals 725 nanometers. The velocity now is 800,000 meters per second. C, again, I have from my equation sheet is 3 times 10 to the 8 meters per second. But notice one important difference here is that it's traveling toward the Earth. So that means my final answer, again, which is the peak wavelength observed, it's not asking for the change, it's asking for what is the wavelength. That's going to now be lambda minus delta lambda. Right? Because it's blue shifted. It's traveling toward the Earth. The wavelength actually has to decrease. So whether you use a plus or a minus is going to depend on whether it's traveling away or toward. Okay, but other than that, we use this exact same rearranged equation to solve for the change in wavelength. So delta lambda equals lambda times v divided by c, which in this case is 725 times 800,000 divided by 3 times 10 to the 8. So let's use our calculator again. 725 times 800,000 divided by, I'm going to use parentheses, 3 times 10 to the 8, close parentheses, enter. 1.933. One thing I hope you notice is that anytime I'm using like a calculation in the denominator or a scientific notation in the denominator, I always use parentheses. Because whenever you're multiplying by something in the denominator or using exponents, to keep it in the denominator, parentheses will help you do that. Otherwise, it could end up being multiplied to the top and just weird stuff happens. So that's why I use parentheses a lot, in the denominator especially. All right, that's delta lambda, so my answer is going to be lambda minus delta lambda, which is 725 minus 1.933. I can't do that in my head. 725 minus 1.933. Okay, 723.067. 067. So that is my answer. 723.067. Okay. So far, so good. Let's take a look at the next one. How many millimeters will a 17 millimeter wavelength radio wave be shifted if the source is traveling away from the observer at 12,000 meters per second? Now, we have to read this carefully and notice that it's asking us how many millimeters will it be shifted. Now, that's not asking us for the new wavelength. It's asking us for the change in wavelength. So this question is a little different than the last one because we don't have to actually add this to the original wavelength. It's just asking how much is it shifted. That's the change in lambda. So I'm going to use the same equation, but I don't have to do the last step. So my starting wavelength here is 17 millimeters. My velocity is 12,000,123 meters per second, and the speed of light is 3 times 10 to the 8th. And again, I'm going to use that rearranged version of the equation, which you, of course, can put on your equation sheet. Delta lambda equals lambda times v divided by c. And I'll just plug in my values here. 17 millimeters times 12 million divided by 3 times 10 to the 8. All All right, and this will give me the change. Let's see what we got. 17 times 12, 1, 2, 3, 1, 2, 3, divided by, open parentheses, 3 times 10 to the 8, close parentheses, enter, 0.68. Notice how these numbers work out pretty good too. We're not getting lots of crazy numbers, nothing really, really big or really, really small. Again, that's a sign that you've done something right. If you're getting something with raised to, if you're getting a value that you have to use scientific notation because it's so big or so small, then chances are you've made an error. All right, let's take a look at the next two questions. Okay, if the peak wavelength of a star at rest is 350 nanometers, but astronomers on Earth observe that it has shifted by 2.25 nanometers, then how fast is it moving? So what are we given here? It looks like we're being told that lambda, the rest wavelength, is 350 nanometers. And then we're being told that it's shifted, delta lambda, by 2.25 nanometers. And what we're being asked to find is what is the velocity. And of course then we know still that c is 3 times 10 to the 8. So it looks to me like we need to do a little algebra and solve for velocity instead. Now remember, the equation we were given on our equation sheet is delta lambda over lambda equals v over c. Well, we need to rearrange this equation to get velocity by itself. So if I multiply both sides by c, the speed of light, this will become velocity equals c times delta lambda over lambda. Okay, well that's another equation. If you wanted to rearrange, to save yourself the algebra, you could put that on your equation sheet. Then you could solve problems like this without having to redo the algebra every time. So let's just plug in our values then. That's just, I'll rewrite the equation here. V equals now speed of light, 3 times 10 to the 8, times delta lambda, 2.25, divided by lambda, 350. Now, velocities here, in order to produce this kind of change in wavelength, it takes a lot of velocity. You notice that in our earlier problems, the velocity was always really quite large. So these values would be quite large as well. So I have 3 times 10 to the 8, enter, times 2.25, enter, divided by 350, enter. And you see I do have quite a large value, 1928571. 1928571. So that's a really big number. But that is the correct answer, and you just put that number right in. 1928571. Keep in mind that, remember, to get a substantial change in the wavelength of light, the source has to be moving really quite fast, especially when it's measured here in meters per second. These astronomical bodies are moving very quickly. So these kinds of problems, when you're solving for speed, you should expect very large numbers. Unless the shift is insanely small, which you see here in the next one. But even that's going to have some significant velocity. Okay, so this problem is saying the peak wavelength of a star at rest is 660 nanometers. So that's our lambda. Astronomers on Earth observe that it has been shifted by, so delta lambda is 0.001 nanometers. And again, our speed of light is 3 times 10 to the 8. So again, I can use this rearranged version to solve for the speed, because it's asking how fast is it moving. That's our speed, so V equals C times delta lambda over lambda. That's 3 times 10 to the 8 times delta lambda, 0.001 over lambda, 660. Let's see what that gets us. I'll write it down below. Okay. 3 times 10 to the 8th, enter, times 0.001, enter, divided by 660, enter. Okay, it's still relatively large. 454 meters per second. Now notice this is not nearly as big as the last one, but see how tiny this shift was compared to this shift, right? It was like 1,000 times smaller. And that's why we get a much smaller velocity. Okay, I just want to highlight that because if you get a really big value for your velocity, it's not necessarily wrong, right? Because some of these are big velocities. Okay, I hope that was helpful to you as you work through not only this practice, but also the chapter quiz.